Welcome, and let yourself settle into this quiet space as we explore the human brain together. There's nothing you need to do but rest here, breathing softly while we journey through human brain facts that reveal the gentle mysteries within your skull. We'll discover surprising facts about the human brain tonight, 100 small windows into this 3-pound universe of consciousness, each fact a whisper of science carrying you towards sleep. If you enjoy this video, please consider liking and leaving a comment below. I'd love to know what topic you'd like to hear about next. It also helps others who enjoy sleepy science explorations to find their way here too, one sleepy soul at a time. Now, let your body grow heavy. Let your thoughts slow and soften, and allow these stories of neurons and networks to guide you gently downward, fact by gentle fact, into the restful darkness where your remarkable brain continues its ceaseless work. The human brain weighs approximately 3 pounds, about the weight of a small cantaloupe resting in your hands. This modest mass, barely heavier than a laptop computer, contains everything you are, every choice you've made, every person you've loved, every song that's moved you to tears. It floats in cerebrospinal fluid within your skull, cushioned and protected like something precious suspended in amber. The brain's weight remains relatively constant throughout adulthood, neither growing nor shrinking significantly under normal circumstances, just maintaining its steady presence through decades of living. If you were to hold a human brain, you'd be surprised by its softness, its delicate texture more like firm gelatin than anything solid, vulnerable and powerful all at once. 3 pounds of matter generating a universe of experience, moment after moment, breath after breath, from your first day until your last. The brain contains roughly 86 billion neurons, each one a tiny messenger in a vast network of whispers. To count them one by one would take you nearly 3,000 years without pause, and yet they all exist together in the small space behind your eyes. These 86 billion cells form a living constellation more complex than any galaxy, each neuron a point of light communicating with thousands of others. The number is so large it defies easy comprehension. More neurons in your head than there are stars in the Milky Way, more connections than there are leaves in the Amazon rainforest. Scientists determined this number through painstaking methods, dissolving brain tissue carefully and counting cell nuclei under microscopes, working for years to arrive at this figure that defines the basic architecture of human thought. 86 billion tiny engines of consciousness, all firing together to create the seamless experience of being you. The brain's fastest neurons can send signals at speeds up to 268 miles per hour through thick, insulated pathways, while the slowest, unmyelinated fibers carry messages at barely 1 mile per hour, a gentle walking pace. This dramatic range means some sensations reach your awareness almost instantly, the sharp touch of something hot arriving in milliseconds, while other signals meander slowly through your nervous system like travelers on a long journey. The fastest pathways are wrapped in myelin, a fatty insulation that works like the rubber coating on electrical wires, letting signals jump quickly from point to point. The slowest fibers carry dull, aching pain and the diffuse sensations of your internal organs, information that doesn't need to arrive quickly, messages that can take their time. Your brain coordinates this symphony of speeds, fast and slow signals arriving in harmony to create your unified experience of the world, moment by moment. The brain uses about 20% of the body's total oxygen supply, even though it represents only 2% of body weight. With every breath you take, 1/5 of that precious oxygen flows directly to your brain, feeding its constant hunger for fuel. This disproportionate demand means your brain is always working, even during the deepest sleep, burning through oxygen to maintain the delicate chemistry of consciousness. The brain cannot store oxygen the way muscles store energy. It needs a continuous supply, moment after moment, or its cells begin to falter within minutes. This is why holding your breath feels so urgent, why your body panics when oxygen runs low, your brain sounding alarms to protect its constant need. 20% of every breath you take belongs to the organ reading these words right now, processing them, finding meaning, creating understanding from symbols on a screen, all powered by the oxygen flowing through your blood this very moment. A single neuron can connect to thousands of other neurons, creating trillions of possible connections. Each cell reaches out through delicate branches called dendrites, touching other cells at junctions called synapses, forming networks of staggering complexity. If you could see these connections, they would look like a forest of infinite intricacy, branches interweaving with branches, creating pathways that shift and change with every new experience. A typical neuron might connect to anywhere from 1,000 to 10,000 other neurons, and those neurons connect to thousands more, creating cascades of communication that ripple through your brain like waves through water. These connections are not fixed but plastic, growing stronger with use, weakening with neglect, constantly reorganizing themselves as you learn and remember and forget. The number of possible connection patterns exceeds the number of atoms in the universe, making your brain's potential configurations essentially infinite, a unique universe that has never existed before and will never exist again. The brain generates about 20 watts of electricity during typical activity, roughly the power needed for a dim refrigerator bulb glowing through the night. This gentle current flows through your neurons constantly, electrical impulses racing along cellular pathways like quiet lightning, too small to feel but powerful enough to generate every thought, every movement, every heartbeat. The electricity your brain produces is not like the current flowing through wires in your walls, but rather the movement of charged particles across cell membranes, sodium and potassium ions flowing in carefully orchestrated patterns. This electrical activity creates the brainwaves that scientists can measure with electrodes placed on your scalp, oscillating patterns that change with sleep and waking, attention and rest. 20 watts of living electricity, enough to power a small light, and yet sufficient to illuminate an entire inner world of sensation, memory, imagination, and dream, all humming quietly in the darkness of your skull as you drift towards sleep. The cerebral cortex, the brain's outer layer, is about 2 to 4 millimeters thick, roughly the depth of 2 stacked pennies. This thin sheet of tissue, barely thicker than cardboard, contains the neural machinery for most of what makes you human, processing sensation, generating movement, creating language and thought. The cortex is organized in 6 layers, each layer containing different types of neurons arranged in columns that function like tiny processing units working in parallel. Despite its thinness, the cortex is so densely packed with cells that it contains the majority of your brain's neurons, billions of them arranged in this remarkably compact space. The cortex wraps around the deeper structures of your brain like a folded blanket, its surface area expanded through countless folds and wrinkles that increase the amount of tissue that can fit within your skull. 2 to 4 millimeters of living tissue, thinner than the screen you're reading from, and yet containing the mechanisms of perception, reason, and self-awareness that define human consciousness. If you could unfold the cerebral cortex, it would cover an area about 2.5 square feet, roughly the size of an extra-large pizza. All those folds and wrinkles that give the brain its characteristic appearance exist to pack this large surface area into the limited space inside your skull. The cortex needs to be large to contain enough neurons for complex processing, but your head can only grow so big, so evolution solved this problem through folding, creating a surface area far larger than the volume it occupies. The pattern of folds is not random, but follows general principles, with certain major fissures appearing in every human brain, landmarks that help neuroscientists navigate this wrinkled landscape. If you could smooth out all those convolutions and spread your cortex flat, you could cover a small table with it, this sheet of living tissue that contains your capacity for language, mathematics, music, and every other distinctly human ability. A pizza-sized piece of you, folded into the space of a grapefruit, working quietly in the darkness to generate the illuminated world of your experience. The brain is about 60% fat, making it the fattiest organ in the human body. This high-fat content is not stored energy like the fat beneath your skin, but rather structural fat, the myelin that insulates neurons and the lipid membranes that form cell walls. The brain needs this fat to function properly, using it to create the electrical insulation that speeds neural signals and to build the flexible membranes that let neurons change shape and form new connections. This is why the brain appears grayish-white rather than red like muscle, the pale color coming from the fatty myelin coating so many of its fibers. The importance of fat to brain function explains why certain dietary fats, particularly omega-3 fatty acids, are so crucial for brain development and health. providing the raw materials for building and maintaining this fatty architecture. 60% fat, a composition that seems almost absurd until you remember that this organ needs to be something other than muscle, something that can transmit electricity at extraordinary speeds while remaining soft and adaptable enough to rewire itself throughout your entire life. Brain cells called astrocytes, shaped like tiny stars, exist in roughly equal numbers to neurons, helping nourish and protect them. These star-shaped cells were once thought to be merely structural, passive scaffolding holding neurons in place, but scientists now understand they play active roles in brain function. Astrocytes wrap around blood vessels and neurons simultaneously, controlling which nutrients pass from blood to brain cells, acting as selective gatekeepers that maintain the brain's delicate chemical environment. They also absorb excess neurotransmitters after neurons finish signaling, cleaning up the space between cells so messages remain clear and distinct. Recent research suggests astrocytes may even participate in information processing themselves, communicating with each other and with neurons in ways we're only beginning to understand. These stellar cells exist in roughly 1-to-1 ratio with neurons throughout most of the brain, a vast population of supporters working quietly to keep your thoughts flowing, your memories forming, your consciousness sustained through every moment of your life. The brain continues developing until approximately age 25, with the prefrontal cortex finishing last. This prolonged development means the brain you have as a teenager is fundamentally different from the brain you'll have in your mid-20s, still growing and reorganizing even after your body has reached its full height. The prefrontal cortex, responsible for planning, impulse control, and weighing consequences, is the slowest region to mature, which helps explain why young adults sometimes struggle with long-term decision-making despite being intellectually capable. During these years of development, the brain is pruning connections, eliminating synapses that aren't being used while strengthening pathways that are frequently activated, sculpting itself based on experience. This extended development period is unique to humans, our brains taking far longer to mature than those of any other species. A long childhood and adolescence allowing time for learning and cultural transmission. 25 years from first breath to full maturity, a quarter century of growing and refining, until finally the architecture settles into its adult form, still capable of change but now fundamentally complete. During REM sleep, the brain is nearly as active as when you're awake. If scientists were to measure your brain's electrical activity during dreams, they would see patterns almost indistinguishable from waking consciousness, waves of activation sweeping across your cortex while your body lies paralyzed and still. This paradoxical state, the brain fully alert while the body rests deeply, is when most vivid dreaming occurs. When you experience narratives and sensations that feel completely real despite being generated entirely from within. During REM sleep, your brain is consolidating memories, processing emotions, making connections between new experiences and old knowledge, working through the day's events in symbolic form. The brain's activity during these periods is so intense that it requires nearly as much oxygen and glucose as waking consciousness, a metabolic demand that explains why sleep is not simply rest, but a different kind of work. Tonight, as you drift into sleep, your brain will light up again and again, creating dreams you may or may not remember, staying active and alive through the darkness, working while you rest. The brain can process images seen for as little as 13 milliseconds, faster than a single blink. In the time it takes you to snap your fingers, your brain can perceive and categorize a visual scene, distinguishing faces from objects, detecting movement and color, extracting meaning from shapes before conscious awareness even begins. This extraordinary speed evolved to keep us safe, allowing instant recognition of threats or opportunities in the visual environment, processing that happens so quickly it seems to bypass thought entirely. Researchers discovered this by flashing images on screens for progressively shorter durations, finding that people could still identify what they'd seen even at these incredibly brief exposures. The brain accomplishes this through parallel processing, different visual areas analyzing color, motion, and form simultaneously rather than sequentially, all the results converging to create a unified perception. 13 milliseconds, barely long enough to register as a moment, and yet sufficient for your brain to capture a scene, name what matters, and prepare a response, all before you consciously realize you've seen anything at all. There is no pain receptor in brain tissue itself, which is why brain surgery can be performed while patients are awake. The brain that processes every ache and injury in your body cannot feel its own damage, cannot sense when it's being cut or manipulated, a strange blindness that allows surgeons to operate on conscious patients. During awake brain surgery, patients can talk with doctors, answer questions, even perform tasks while surgeons work directly on their exposed brain tissue, using the patient's responses to map which areas control which functions. The skull and the membranes surrounding the brain do have pain receptors, which is why headaches hurt, but the brain itself is insensate to direct touch and pressure. This lack of pain sensation inside the brain means tumors can grow to dangerous sizes before causing symptoms, expanding silently until they press on pain-sensitive structures or interfere with function. The organ that creates all your pain, that interprets every injury and sends distress signals through your body, sits in quiet numbness, unable to feel itself, paradoxically vulnerable because it cannot detect its own damage. The human brain begins forming in the womb just 3 weeks after conception. At this impossibly early stage, when the embryo is barely the size of a poppy seed, cells are already organizing into what will become the nervous system, the neural tube beginning to form along what will be the baby's back. This is the starting point of the brain, a simple structure that will fold, expand, and differentiate over the coming months into the intricate organ of consciousness. By week 5, the brain begins dividing into its major regions, the forebrain, midbrain, and hindbrain emerging as distinct structures. By week 7, neurons are being born at an astonishing rate, sometimes as many as 250,000 per minute, a biological explosion of cellular production. Throughout pregnancy, the developing brain is extraordinarily sensitive to the mother's environment, to nutrition and toxins, stress and safety, all of which can influence how neurons migrate and connect. 3 weeks after conception, long before most people know they're pregnant, the brain has already begun its long journey toward consciousness, growing in darkness, preparing for light. By age 2, a child's brain is already 80% the size of an adult brain. This rapid early growth reflects the extraordinary development happening in the first years of life, when a baby's brain is forming connections at a rate that will never be matched again. At birth, the brain is only about 25% of its adult size, but it grows more rapidly than any other organ, doubling in size in the first year and reaching that 80% mark just 12 months later. This growth is not primarily about adding new neurons. Most of those are already present at birth, but rather about neurons growing larger, extending their branches, forming connections, and wrapping themselves in myelin. The 2-year-old brain, though small enough to fit in your hands, already contains most of the neural infrastructure it will carry through life, the fundamental architecture already in place even as decades of refinement lie ahead. 80% complete at 2 years old, and yet still so much development to come. The brain both nearly finished and just beginning its long maturation into adulthood. The left and right hemispheres of the brain are connected by a bundle of 200 to 250 million nerve fibers called the corpus callosum. This dense bridge of tissue allows the two halves of your brain to communicate constantly, sharing information so the left hand knows what the right is doing, creating a unified experience from two separate processing centers. The corpus callosum is the largest white matter structure in the brain, a highway of fibers carrying signals back and forth across the midline dozens of times per second. When surgeons cut the corpus callosum to treat severe epilepsy, patients develop what's called split brain syndrome, where the two hemispheres can no longer share information directly, leading to strange disconnections between what each half knows and controls. In normal brains, this massive bundle ensures constant integration, the verbal left hemisphere communicating with the more spatial right hemisphere, both sides contributing to every complex thought and action. 200 million fibers, each one a thread in the fabric that makes you feel like a single coherent self rather than two separate beings sharing a skull. Forgetting is an active process controlled by specific neurons that help clear unnecessary memories. Your brain doesn't forget through simple decay or passive fading, but rather through deliberate mechanisms that identify and weaken certain memory traces while preserving others. Scientists have discovered neurons that actively promote forgetting by releasing chemicals that instruct other cells to dismantle memory connections, pruning away information that no longer serves you. This active forgetting is not a flaw but a feature. preventing your memory from becoming cluttered with trivial details that would make it harder to retrieve important information when you need it. The brain must balance remembering and forgetting, holding on to what matters while releasing what doesn't, a constant curatorial process happening below conscious awareness. Every detail you've forgotten, every name that slipped away, every event that faded from memory may have been actively cleared by these specialized neurons, making space for new experiences, new learning, new memories that will serve you better than whatever they replaced in the limited storage of your mind. The brain's hippocampus, crucial for memory, can grow new neurons throughout your entire life. For decades, scientists believed neurogenesis, the birth of new brain cells, stopped in early childhood, leaving you with a fixed number of neurons that could only decline with age. But research in the late 1990s overturned this dogma, showing that the hippocampus continues generating thousands of new neurons every day well into old age. These new neurons integrate into existing memory circuits, contributing to the formation of new memories and potentially helping distinguish between similar experiences. The rate of neurogenesis can be influenced by lifestyle, increasing with physical exercise, learning, and enriched environments, declining with stress and poor sleep. This means you're not stuck with the brain you have, that new neurons are being born in your hippocampus right now, today, waiting to be woven into the fabric of your memory systems. Throughout your entire life, from birth to your final days, your brain retains this capacity for cellular renewal, for generating new possibilities, for growing in the same organ that holds every memory you've ever made. Your brain uses approximately 20% of your total blood supply with every heartbeat. With each pulse of your heart, 1/5 of the blood that just left your heart's left ventricle flows directly to your brain through carotid and vertebral arteries, delivering oxygen and glucose to billions of hungry cells. This massive blood flow is necessary because brain cells cannot store energy the way muscle cells can. They need a constant supply of fuel arriving moment after moment in the bloodstream. The brain receives about 15% of the heart's output in terms of blood volume, but it extracts oxygen so efficiently that it ends up using 20% of the body's total oxygen consumption despite its small size. This high blood flow is why strokes are so dangerous. Even brief interruptions to this supply can kill neurons within minutes, permanently destroying the circuits they were part of. Every heartbeat sends this wave of nourishment to your brain, a rhythmic delivery system that has been sustaining your consciousness since before you were born, keeping you alive and aware through every moment of your existence. The average adult brain contains about 78% water, more liquid than solid. The brain's tissue is not firm and dense, but rather soft and almost gelatinous, mostly water held in careful arrangement by proteins and fats. This high water content is essential for the brain's electrochemical signaling, providing the medium in which ions can flow and neurons can communicate. Dehydration affects brain function noticeably. Even mild fluid loss can impair concentration, mood, and memory, shrinking brain tissue slightly and disrupting the delicate balance of electrolytes that neurons depend on. The water in your brain is not static but constantly flowing, cerebrospinal fluid circulating around and through brain tissue, blood plasma seeping through capillary walls, bringing nutrients and carrying away waste. When you drink water, some of it becomes part of your brain within minutes, joining the vast ocean of fluid that makes up most of what you are, the liquid foundation of consciousness itself. 78% water, and yet somehow this mostly liquid organ generates the solid experience of being you, proof that consciousness emerges not from any particular substance but from the patterns of interaction between simple parts. Chronic stress can actually shrink the brain's prefrontal cortex while enlarging the amygdala. When stress becomes constant and unrelenting, it physically changes brain architecture, weakening areas responsible for rational thought and decision-making while strengthening areas that process fear and emotional reactivity. The prefrontal cortex, which helps you plan, regulate emotions, and think through consequences, actually loses volume under chronic stress, its neurons shrinking and pulling back their branches. Meanwhile, the amygdala, the brain's alarm system for detecting threats, grows larger and more reactive, becoming oversensitive to potential dangers and triggering more frequent stress responses. These changes make it harder to think clearly and easier to feel anxious, creating a feedback loop where stress breeds more stress. Fortunately, these structural changes are not permanent. The brain can recover when stress diminishes, the prefrontal cortex regrowing and the amygdala calming, demonstrating again the brain's remarkable plasticity. The stress you carry changes the very organ trying to manage it, shaping your brain in ways that can help you survive immediate threats but harm you when threats become chronic and inescapable. The brain can survive for about 6 minutes without oxygen before permanent damage begins. This narrow window is why emergency responders work so urgently to restore breathing and circulation, why every second matters in cardiac arrest, why drowning victims can sometimes be revived even after their hearts have stopped. The brain's enormous energy demands mean it burns through its small oxygen reserves almost immediately when blood flow stops, neurons beginning to falter within seconds. After about 4 to 6 minutes without oxygen, brain cells start dying, the damage initially affecting the most oxygen-hungry regions like the hippocampus and cerebral cortex. If oxygen is restored quickly enough before this critical threshold, the brain can recover fully, resuming normal function as if the interruption never happened. But once that 6-minute mark passes, each additional minute increases the likelihood of permanent injury, of memories lost, abilities diminished, consciousness forever changed. 6 minutes, barely long enough to watch a short video, and yet the difference between full recovery and catastrophic brain damage, a reminder of how fragile this organ is despite its remarkable resilience in other ways. During pregnancy, a woman's brain actually shrinks slightly and reorganizes to enhance maternal bonding. This temporary reduction in volume, particularly in areas involved in social cognition, is not damage, but rather refinement. The brain pruning connections to become more efficient at reading infant cues and responding to a baby's needs. The grey matter decreases in regions that help mothers interpret their baby's mental states, and paradoxically, this reduction correlates with stronger maternal attachment and more sensitive caregiving. Researchers found that these changes can last for at least 2 years after birth, representing a significant reorganization of brain function that helps mothers bond with and care for their infants. The brain is literally reshaping itself to prioritize the baby's needs, becoming more efficient at the specific cognitive tasks motherhood requires while temporarily reducing capacity in less relevant areas. This neurological transformation is one more example of the brain's plasticity, its ability to restructure itself in response to new demands, growing and shrinking in different regions to optimize for changing life circumstances, even something as profound as becoming a parent. The brain's white matter tracts act like information highways, with some bundles containing over 1 million individual nerve fibers running parallel like cables in a vast underground network. These white matter pathways connect distant brain regions, allowing different areas to communicate and coordinate their activities. The largest white matter bundles, like the corpus callosum or the corona radiata, carry millions of signals simultaneously, each fiber transmitting its own message while running alongside countless others in organized bundles. These tracts are white because of myelin, the fatty insulation coating each fiber, giving these regions their pale appearance and their collective name. Damage to white matter disrupts communication between brain regions even when the regions themselves are intact, like cutting telephone cables between cities that can no longer talk to each other. The brain's white matter increases throughout childhood and adolescence as neurons become increasingly myelinated, improving the speed and efficiency of neural communication. 1 million fibers in a single bundle, all of them necessary, all of them contributing to the seamless integration that makes your brain function as a unified whole rather than a collection of isolated parts. The brain shifts its focus between different thoughts approximately 6,000 times per day, a constant, gentle movement of attention. Your mind is not still but perpetually in motion, flowing from one focus to another, noticing, considering, then releasing and moving on to the next object of awareness. These transitions between thoughts are not usually conscious decisions but rather spontaneous shifts driven by both external stimuli and internal mental processes. Some transitions are triggered by sensory input, a sound or movement catching your attention and pulling your thoughts in a new direction. Others arise from within, memories or associations or random neural activity bringing new content into awareness without any external prompt. The brain seems to be wired for this constant shifting, unable or unwilling to hold perfectly still on a single thought for more than brief periods. 6,000 transitions each day from morning until night, your attention dancing from thought to thought, creating the flowing stream of consciousness that fills your waking hours with an ever-changing parade of perceptions, memories, plans, and daydreams. The human brain can store an estimated 2.5 petabytes of information, equivalent to about 3 million hours of television. This staggering storage capacity, if it were a digital device, would require millions of standard smartphones to match, all of that contained in the 3 pounds of tissue inside your skull. The estimate comes from calculating the number of synapses in the brain and the information each synapse could theoretically encode through variations in connection strength. Of course, the brain doesn't store information like a computer does. It doesn't save files or record video, but rather encodes memories through patterns of connections between neurons, distributed representations that make precise capacity calculations somewhat speculative. Nevertheless, the brain's ability to hold a lifetime of experiences, skills, faces, facts, stories, songs, and sensations in such a compact space remains one of nature's most impressive engineering achievements. 2.5 petabytes, enough to record every moment of a human life in high definition and still have room left over, all stored not on hard drives or memory chips, but in the living tissue of your brain, accessible through thought alone, persistent across decades, surviving in an organ that rewrites itself constantly while somehow maintaining continuity of self. Brain freeze from cold foods occurs when blood vessels in the roof of your mouth rapidly constrict, then dilate. That sharp, temporary headache you feel when eating ice cream too quickly is your brain's alarm system responding to sudden cold stimulating nerves in your palate. When cold touches the roof of your mouth, blood vessels there constrict to conserve heat, then dilate rapidly as a protective response. This sudden change triggering pain receptors that send signals along the trigeminal nerve to your brain. The pain is referred, meaning you feel it in your forehead even though the problem originates in your mouth, a quirk of how pain signals are processed and interpreted. The headache typically lasts only 30 to 60 seconds as your mouth warms and blood flow normalizes, the shortest of all headache types. Brain freeze is harmless despite how intensely uncomfortable it can feel, just your body's defensive systems overreacting to an unusual stimulus, the cold shock triggering warning signals that quickly fade when the perceived threat passes. A moment of pain in exchange for frozen treats, a small price for the pleasure of cold sweetness on a warm day. The sensation of déjà vu may result from a brief misfiring in the brain's memory systems. That uncanny feeling of having lived through a moment before, of experiencing something for the first time while being certain you've experienced it previously, might occur when memory formation and memory retrieval circuits activate simultaneously by accident. The brain normally keeps these processes separate, encoding new experiences into memory through one set of pathways while retrieving old memories through another, but occasionally the signals get crossed and a present experience gets tagged as a memory even as it's happening. Another theory suggests déjà vu occurs when one hemisphere processes information slightly before the other, creating a tiny delay that makes the second processing feel like a repetition. Most people experience déjà vu occasionally, especially when tired or stressed. These fleeting moments of temporal confusion that remind us how actively the brain constructs our sense of time and experience. The feeling typically lasts only seconds before fading, leaving you with the strange sense that reality briefly flickered, that time folded back on itself before everything returned to normal and the moment became simply another memory forming in the usual way. Your brain begins to slow its processing speed after age 24, though wisdom and experience continue growing. This slowing is subtle and gradual, difficult to notice in daily life, but measurable in laboratory tests that assess reaction time and processing speed. The brain remains plastic and capable of learning throughout life, but the raw computational speed, the quickness with which it can process new information, peaks in the early 20s and then begins a long, slow decline. This doesn't mean cognitive decline. Older adults often perform better on complex reasoning tasks despite slower processing, compensating for reduced speed with better strategies and deeper knowledge. The brain trades speed for sophistication as it ages, becoming less like a fast computer and more like an expert advisor who takes time to consider all angles before responding. Crystallized intelligence, the accumulated knowledge and wisdom from years of experience, continues increasing well into middle age and sometimes beyond. Even as fluid intelligence, the ability to solve novel problems quickly, gradually diminishes. 24 years old, the peak of processing speed, young enough that most people haven't yet realized their minds will never be quite this quick again, old enough to have learned how little raw speed matters compared to knowing what to do with it. The human brain's frontal lobe contains neurons packed with exceptional density and complexity of connections, creating networks more intricate than those of our closest primate relatives. While the frontal lobe's size relative to the rest of the brain is similar in humans and great apes, the quality of neural architecture within that space differs dramatically, with human frontal cortex containing more processing power per cubic millimeter than any other primate brain. This density and complexity of connections rather than sheer size explains humanity's unique cognitive abilities, our capacity for abstract thought, long-term planning, complex language, and cultural transmission. The frontal lobe, particularly the prefrontal cortex, expanded relatively recently in evolutionary terms, its current form emerging only in the last few 100,000 years of human evolution. These networks allow you to imagine distant futures, to plan for contingencies that may never happen, to consider how your actions will appear to others, to hold multiple possibilities in mind and choose between them based on abstract principles. The exceptional density of connections in this small region, this architectural refinement rather than simple enlargement, makes the difference between human cognition and even our closest evolutionary relatives, all the art and science and philosophy emerging from these particularly well-connected cells. Phantom limb sensations occur because the brain maintains a map of the body even after parts are removed. The brain's sensory cortex contains a representation of your entire body surface, with specific regions dedicated to processing sensation from each part, and this map doesn't immediately disappear when the corresponding body part is lost. After amputation, the brain region that once received signals from the missing limb remains present and active, and when neighboring regions accidentally activate it, the person feels sensations that seem to come from the limb that's no longer there. These phantom sensations can be incredibly vivid. People report feeling their missing hand clench or their absent foot itch, the brain creating experiences of body parts that exist only in neural maps. Sometimes the phantom sensations are painful, the brain generating distress signals from a limb that can't hurt because it no longer exists, a cruel trick of body mapping that persists because the brain cannot easily revise its fundamental architecture. Treatment approaches like mirror therapy work by giving the brain new visual input to override the faulty map, tricking it into reorganizing and sometimes reducing phantom pain. The map in your brain is older and more fundamental than your actual body, a template that persists even when the territory it represents has been lost. The brain can rewire itself through neuroplasticity, forming new connections throughout life. This capacity for change allows you to learn new skills, recover from injuries, and adapt to changing circumstances even in old age. The brain constantly sculpting itself based on experience. Every time you practice something, whether playing piano or speaking a new language, you're physically changing your brain, strengthening certain synapses while weakening others, gradually shifting the landscape of connections. Neuroplasticity is most dramatic in childhood when the brain is developing rapidly, but it never entirely disappears. Older brains retain the ability to form new connections and new memories, to learn and adapt just more slowly than young ones. Brain injuries demonstrate plasticity dramatically, with patients sometimes recovering lost functions as other brain regions learn to take over the jobs of damaged areas, finding new pathways to accomplish old tasks. This rewiring isn't always positive. Chronic pain can result from maladaptive plasticity that amplifies pain signals, creating suffering that persists long after the original injury has healed. The brain you have today is different from the brain you had last year, changed by everything you've learned and done, and it will continue changing until your final day, never fixed, never finished, always becoming something new. Laughing activates 5 different areas of the brain simultaneously. When something strikes you as funny, motor areas in your frontal lobe prepare the physical act of laughing. Your limbic system processes the emotional pleasure. Your prefrontal cortex analyzes the humor to understand why it's funny. Your sensory cortex receives feedback from your body as you laugh, and your brainstem coordinates the breathing patterns that produce laughter's characteristic sound. This widespread activation explains why laughter is such a whole-body, whole-brain experience, engaging cognition and emotion and movement all at once. The brain seems to have dedicated circuits for humor detection and response, recognizing incongruity or surprise or wordplay, and triggering this characteristic reaction that's nearly universal in humans. Laughter is also contagious because your brain has mirror neurons that activate when you see someone else laughing, creating an impulse to laugh yourself even if you don't know what's funny. 5 brain regions working together to produce those moments of spontaneous mirth that punctuate your days, a complex neural symphony that results in simple joy, your brain coordinating itself to create and share amusement. The cerebellum, though only 10% of brain volume, contains over 50% of the brain's total neurons. This dense packing of cells in the small structure at the back of your brain reflects the cerebellum's crucial role in coordinating movement and maintaining balance. The cerebellum contains roughly 69 billion neurons compared to the cerebral cortex's 16 billion, most of them tiny granule cells packed densely in the cerebellar cortex's distinctive layers. These neurons work together to fine-tune movements in real time, taking the motor commands from your cerebral cortex and adjusting them based on sensory feedback, smoothing out your actions so they're coordinated and precise rather than jerky and imprecise. Damage to the cerebellum doesn't cause paralysis but rather ataxia, the loss of movement coordination, making it difficult to walk straight or reach accurately for objects even though strength remains intact. Recent research suggests the cerebellum also contributes to cognitive functions like language and attention, its role extending beyond just motor control into broader aspects of timing and prediction. 10% of volume holding 50% of neurons, a monument to efficient packing, the cerebellum working quietly in the back of your brain to make every movement smooth, every step balanced, every gesture controlled and graceful. Your brain produces new brain cells through neurogenesis, particularly during exercise. Physical activity stimulates the production of growth factors that promote the birth and survival of new neurons in the hippocampus, creating more cells available for learning and memory formation. Exercise increases blood flow to the brain, delivers more oxygen and nutrients, and triggers the release of proteins like BDNF, brain-derived neurotrophic factor, which supports neuron growth and synaptic plasticity. Studies show that regular aerobic exercise can actually increase hippocampal volume in older adults, partially reversing the age-related shrinkage that normally occurs, demonstrating that physical movement has direct effects on brain structure. The new neurons born during exercise don't just sit idle but integrate into existing circuits, contributing to memory formation and potentially improving mood and cognitive function. This means that when you go for a run or take a long walk, you're not just exercising your body but actively promoting brain health, stimulating cellular renewal in the organ responsible for every thought and memory. Movement creates neurons, physical activity generating the raw materials of mental life, another reminder that brain and body are not separate but intimately connected parts of a single living system. The brain operates on the same amount of power as a 10-watt light bulb when resting. This modest energy consumption is remarkable considering the incredible computational work the brain performs continuously, processing sensory input, maintaining consciousness, coordinating body functions, all running on less power than a standard LED bulb. The brain achieves this efficiency through massively parallel processing, billions of neurons working simultaneously on different aspects of a problem rather than handling tasks sequentially like a computer. Each neuron operates very slowly compared to electronic components, firing at most a few hundred times per second compared to computers that operate at billions of cycles per second, but the brain compensates through having billions of neurons all working at once. When the brain becomes highly active during intense mental work or complex tasks, its power consumption can increase to 20 to 25 watts, still remarkably efficient for the amount of work being done. This low power requirement allowed brains to evolve to their current size without requiring impossibly large bodies to feed them, the energy cost remaining manageable even as brain size increased. 10 watts of power generating an entire universe of experience, thoughts and feelings and memories all emerging from less energy than it takes to light a closet. Proof that consciousness requires less power than we might imagine. Multitasking is largely a myth. The brain rapidly switches between tasks rather than processing them simultaneously. When you think you're doing two things at once, what's actually happening is your brain is alternating attention between them very quickly, focusing briefly on one task, then switching to the other and back again. This constant switching comes with costs, each transition requiring mental effort and time, which is why multitasking typically reduces performance on both tasks compared to doing them one at a time. The brain can handle some automatic processes simultaneously with conscious tasks. You can walk while talking because walking has become automatic and doesn't require conscious attention. But trying to consciously process two different streams of information at once exceeds the brain's capacity. Brain imaging studies show that when people attempt to multitask, different brain regions activate sequentially rather than simultaneously, the neural traffic light switching between tasks, never truly doing both at once. The feeling of successful multitasking is an illusion. Your brain switching so rapidly that it creates the subjective impression of simultaneity while actually fragmenting your attention. Single tasking, giving full attention to one thing at a time, is not only more effective but also less mentally draining, allowing the brain to work with its natural limitations rather than fighting against them. The average human brain increases about 3 times in size during the first year of life. The newborn brain weighs approximately 350 to 400 grams at birth and grows to roughly 1,000 grams by the first birthday, a period of explosive growth unmatched in any other stage of life. This tripling in size reflects both the growth of existing neurons, which extend their branches and form connections, and the development of support structures like blood vessels and glial cells. During this first year, the brain is forming synapses at an astounding rate, creating up to 2 million new connections per second at peak periods, building the vast network of neurons that will support all future learning. The infant brain is also beginning to myelinate neurons, wrapping them in insulation that speeds signal transmission, starting with the most essential pathways for survival and gradually working outward to more complex functions. This rapid growth requires enormous energy, which is why babies need to eat so frequently and sleep so much, their growing brains consuming a huge proportion of their daily calories. 3 times larger in just 12 months, from a quarter pound to more than 2 pounds of living tissue, the foundation of consciousness being laid down in those early months through growth that will never again be so rapid or so total. Your brain's grey matter peaks in volume around age 11 for girls and between ages 12 and 14 for boys before pruning begins. This peak represents the maximum number of synaptic connections your brain will ever have, billions upon billions of potential pathways created during childhood and early adolescence. After this peak, the brain begins a long process of pruning, eliminating connections that aren't being used regularly while strengthening those that are frequently activated, sculpting itself based on experience and need. This pruning is not a loss but a refinement, the brain becoming more efficient by eliminating redundant or unnecessary connections, like a sculptor removing stone to reveal the form within. The timing difference between girls and boys reflects broader patterns of brain development, with female brains typically maturing faster than male brains in many regions. The pruning process continues through adolescence and into the early 20s, gradually reducing grey matter volume while increasing the quality and efficiency of remaining connections. Peak volume at 11 or 13 years old, more raw material than you'll ever have again, followed by decades of careful editing, the brain cutting away the unnecessary to strengthen what remains, becoming not larger but more refined, not more connected, but more precisely wired for the life you're actually living. The brain can process information as fast as 120 meters per second in some neural pathways. This extraordinary speed, over 250 miles per hour, allows your brain to react to events almost instantly, the time between sensation and response compressed into milliseconds. These fastest pathways are the thickest, most heavily myelinated fibers in your nervous system, carrying urgent information that requires immediate response, like signals about sudden pain or loss of balance. The speed varies dramatically between different types of neurons, with the fastest being large motor neurons that control muscles and sensory neurons that detect touch and position, while slower fibers carry less urgent information like dull pain or temperature. This variation in speed means different aspects of a single experience arrive at your brain at different times. The pressure of something touching your skin arriving before the temperature, sharp pain arriving before the dull ache, all of them stitched together by your brain into a seamless perception, 120 meters per second, fast enough that the signal can travel from your toe to your brain in less than 1/50th of a second, so quick that your conscious mind experiences the sensation and the reaction as nearly simultaneous, though in reality they're separated by these tiny fractions of time that the brain erases to create the illusion of instantaneous awareness. Sleep deprivation for just 24 hours can reduce overall brain function by up to 40%. Missing a single night of sleep impairs your brain's performance dramatically, affecting attention, memory, decision-making, and emotional regulation in measurable ways. Brain imaging shows that sleep deprivation reduces activity in the prefrontal cortex, the region responsible for complex reasoning and impulse control, while increasing activity in emotional centers like the amygdala, making you more reactive and less rational. The tired brain struggles to form new memories, the hippocampus becoming less efficient at encoding experiences into long-term storage, which is why you often can't remember much from times when you were severely sleep-deprived. Reaction times slow, attention wanders, and the ability to focus on tasks deteriorates, the cumulative effect being comparable to having a blood alcohol level of 0.05%, nearly legally drunk in some jurisdictions. The brain needs sleep not just for rest, but for essential maintenance work, clearing metabolic waste, consolidating memories, and pruning unnecessary connections, all processes that can only happen efficiently during sleep. 24 hours without sleep, just one night missed, and your brain is already functioning at 60% capacity or less, a dramatic reminder that sleep is not optional but essential for normal cognitive function. The brain's visual processing center occupies about 30% of the cortex compared to 8% for touch and 3% for hearing. This enormous allocation of neural real estate to vision reflects how dependent humans are on sight for navigating and understanding the world. The visual cortex at the back of your brain is organized in a hierarchy, with early areas processing simple features like edges and colors, while later areas combine this information to recognize objects, faces, and scenes. Vision requires massive computational power, your brain processing millions of pixels of information 10 or more times per second, extracting patterns and meaning from constantly changing visual input. This large visual cortex allows humans to see in extraordinary detail and color, to recognize faces at a glance, to read text, to navigate complex environments, all tasks that require extensive neural processing to accomplish. The dominance of vision in human perception means that what you see often overrides other senses, your brain trusting visual information more than touch or hearing when they conflict. 30% of your cortex dedicated to sight, nearly a third of your brain's processing power devoted to interpreting the light entering your eyes, transforming photons into meaning, raw sensation into the rich visual world you experience moment by moment. Mirror neurons in the brain fire both when you perform an action and when you watch someone else perform it. These neurons, discovered accidentally in monkeys and later found in humans, create a neural resonance between self and other, allowing your brain to simulate others' actions internally. When you watch someone reach for a cup, mirror neurons in your motor cortex activate the same way they would if you were reaching for the cup yourself, creating a kind of neural empathy, a direct understanding of others' actions through internal simulation. This mirroring system may underlie your ability to understand others' intentions, to learn by imitation, to feel empathy for others' experiences, creating a bridge between individual minds. The mirror system responds not just to actions, but to the intentions behind actions, activating differently when you watch someone grasp a cup to drink versus grasping the same cup to move it away. Some researchers believe that dysfunction in mirror neuron systems might contribute to conditions like autism, where understanding others' intentions and emotions can be difficult. These neurons create a shared neural space between you and others, firing when you act and when you observe action, blurring the boundary between self and other in the circuits of your brain, making social connection and understanding possible through neural resonance. The brain releases dopamine during pleasant experiences, creating pathways for habit formation. Dopamine is often called a pleasure chemical, but it's more accurately a learning signal that marks certain actions and experiences as worth repeating. When something good happens, unexpectedly finding money on the sidewalk or tasting delicious food, dopamine neurons fire rapidly, And this burst of dopamine strengthens the neural pathways that led to that outcome, making you more likely to repeat those behaviors in the future. This system evolved to help animals learn which actions lead to survival benefits like food and safety. But in modern environments, it can be hijacked by artificial rewards like drugs, gambling, or social media, which trigger dopamine release more powerfully than natural rewards. The anticipation of reward can release more dopamine than the reward itself, which is why waiting for something pleasant can feel so good, and why the possibility of reward motivates behavior so effectively. Over time, repeated dopamine release in response to the same behavior creates habits, automatic patterns that run with minimal conscious thought, your brain having learned through chemical reinforcement that these actions are worth doing. Dopamine flowing through your reward circuits, teaching your brain what to pursue and what to repeat, shaping your behavior through the simple mechanism of making certain actions feel good, creating the habits that structure your days without your conscious awareness. Your brain can distinguish between thousands of different smells, connecting them deeply to memory. The olfactory system has direct connections to the hippocampus and amygdala, bypassing the thalamus unlike other senses, which creates the strong link between smell and emotional memory that you've probably noticed when a particular scent suddenly transports you to a specific moment from your past. Humans can detect at least 1 trillion different odors according to recent research, a far greater range than scientists previously suspected, with some people able to distinguish even more depending on their genetics and experience. Each smell is detected by a combination of hundreds of different receptor types in your nose, creating a pattern of activation that your brain interprets as a specific odor, like a combination lock where each smell is a unique code. The subjective experience of smell is hard to describe in words. Most languages lack the vocabulary for odors that they have for colors or sounds, making smell a sense that's deeply felt but difficult to communicate. A familiar smell can trigger cascades of memory and emotion instantly. The scent of rain on hot pavement or your grandmother's perfume bringing back entire scenes from years ago, proof that smell and memory are intertwined in the architecture of your brain. The amygdala, an almond-shaped structure, processes fear and emotional memories with particular intensity. This small region deep in the temporal lobe acts as your brain's alarm system, constantly scanning for threats and triggering rapid emotional responses before conscious thought can intervene. When the amygdala detects danger, it can initiate a fear response in milliseconds, releasing stress hormones and activating fight or flight systems throughout your body before you consciously realize what scared you. The amygdala is especially active during fear conditioning, when you learn to associate neutral stimuli with danger, creating powerful emotional memories that can last for years or even a lifetime. Emotional events, particularly frightening or stressful ones, are remembered more vividly than neutral events because the amygdala enhances memory formation in the hippocampus when strong emotions are present. This is why you can remember exactly where you were during major emotional events while forgetting countless ordinary moments. The amygdala can become overactive in anxiety disorders and PTSD, seeing threats where none exist and triggering fear responses to harmless stimuli that have become associated with past trauma. An almond-sized cluster of neurons wielding enormous influence over your emotional life, capable of overriding rational thought when it perceives danger, your brain's early warning system constantly vigilant even while you sleep. Myelin, a fatty substance that insulates neurons, increases the speed of neural transmission by up to 100 times. Without myelin, neural signals would crawl along at a walking pace, but with full myelination they can race at highway speeds, allowing rapid communication between distant brain regions. Myelin is produced by specialized cells called oligodendrocytes in the brain and Schwann cells in the peripheral nervous system, which wrap around axons like insulation around wires, preventing signal loss and allowing faster transmission. The process of myelination continues through childhood and adolescence, with different brain regions becoming myelinated at different times, which partially explains why certain cognitive abilities develop slowly over years. White matter gets its color from myelin, and the increase in white matter during development reflects this ongoing myelination process that gradually speeds up neural communication. Diseases like multiple sclerosis destroy myelin, causing the devastating symptoms that result when neural signals slow down or fail to transmit properly, demonstrating how essential this fatty insulation is for normal brain function. Myelin might seem like a simple insulator, but it's one of the crucial innovations that allowed vertebrate brains to become large and complex, enabling fast communication across distances that would otherwise be impossibly slow, your thoughts traveling at 100 times the speed they could without this molecular innovation. The brain's default mode network activates during rest and daydreaming, helping process experiences. When you're not focused on any particular task, when your mind wanders freely, this network of brain regions becomes active, different from the networks that activate during focused attention. The default mode network includes the medial prefrontal cortex, posterior cingulate cortex, and regions of the temporal and parietal lobes, all working together during rest to consolidate memories, imagine future scenarios, and think about yourself and others. This network was discovered accidentally when researchers noticed certain brain regions that were more active during rest than during tasks, contradicting the assumption that resting brains were simply idle. The default mode network appears to be crucial for creativity, self-reflection, and the kind of spontaneous thought that leads to insights and problem-solving, suggesting that daydreaming isn't wasted time but rather a different kind of productive mental work. People with depression often show altered default mode activity, with the network becoming overactive and generating repetitive negative thoughts about the self and past experiences. The balance between task-focused networks and the default mode network may be important for mental health, too much time in either state potentially leading to problems, the healthy brain switching fluidly between focused attention and restful mind wandering. Synesthesia, where senses blend together, occurs when normally separate brain regions communicate unusually. People with synesthesia might see colors when they hear music, taste shapes, or experience numbers as having specific colors, their senses crossing in ways that create unique perceptual experiences. This blending happens because of unusual connections between sensory areas in the brain, pathways that exist in everyone during early development but are usually pruned away, persisting in people with synesthesia and creating these cross-sensory experiences. Synesthesia runs in families and appears to have a genetic component, suggesting it results from differences in how the brain develops rather than from learning or experience. The phenomenon is consistent for individuals. A person who sees the letter A as red will always see it as red, suggesting these are genuine perceptual experiences rather than associations or metaphors. Brain imaging confirms that when a synesthete experiences color-number synesthesia, their visual cortex activates in response to numbers just as it would to actual colors. Synesthesia offers a window into how the brain constructs perception, showing that the boundaries between senses are not absolute but maintained through active inhibition of connections that exist but are normally suppressed, proving that sensory experience is constructed by the brain rather than being a direct readout of external reality. The brainstem controls automatic functions like breathing and heartbeat without conscious thought. This ancient structure at the base of your brain connecting to the spinal cord regulates the most essential functions that keep you alive moment by moment, working ceaselessly without any need for conscious attention. The medulla oblongata controls breathing rhythm and heart rate. The pons helps regulate sleep and arousal, and the midbrain coordinates reflexes and movement, all of them operating autonomously beneath awareness. These automatic controls mean you can sleep without forgetting to breathe, can focus on reading without having to remember to make your heart beat. The brain stem maintaining life support systems no matter what your conscious mind is doing. Damage to the brainstem is often fatal or catastrophic because these functions cannot be taken over by conscious effort. You cannot will yourself to breathe if the breathing center is destroyed. These reflexes either work automatically or not at all. The brainstem represents the oldest part of the brain evolutionarily, structures that were present in our distant ancestors and remain largely unchanged because they solve fundamental problems that all vertebrates face. Every breath you take without thinking, every heartbeat that comes without effort, testifies to the brainstem working perfectly in the background, the foundation upon which all higher brain functions rest, maintaining the basic rhythm of being alive. Your brain continues forming and pruning neural connections based on which pathways you use most frequently. This ongoing process, called synaptic pruning, follows a simple principle. Use it or lose it. Connections that are frequently activated grow stronger, while those that are rarely used gradually weaken and disappear. The brain can't maintain all possible connections simultaneously. Doing so would require impossible amounts of energy and space, so it constantly optimizes, strengthening useful pathways while eliminating redundant or unnecessary ones. This pruning is most dramatic during adolescence but continues throughout life, your brain constantly sculpting itself based on your experiences and behaviors. The principle explains why skills need practice to maintain, why languages you don't use fade from memory, why old habits are hard to break. The neural pathways for these behaviors either growing stronger through use or weakening through neglect. Learning creates new connections while forgetting eliminates old ones, not randomly, but based on what you actually need. The brain efficiently allocating its resources to support your current life, rather than maintaining every pathway it has ever formed. Your brain tomorrow will be slightly different from your brain today, shaped by what you do and think, constantly becoming a more perfect tool for the life you're actually living rather than some theoretical life requiring different skills and knowledge. The thalamus acts as the brain's relay station, directing sensory information to appropriate processing centers. Almost all sensory information from your body passes through the thalamus before reaching the cortex, vision, hearing, touch, and taste, all flowing through this central hub that sorts and directs incoming signals. The thalamus doesn't just passively relay information but actively filters it, deciding what's important enough to pass along and what can be ignored, acting as a gatekeeper that prevents the cortex from being overwhelmed by sensory data. Different regions of the thalamus connect to different cortical areas, creating organized pathways that ensure visual information reaches visual cortex, auditory information reaches auditory cortex, maintaining the brain's careful organization. The thalamus also plays a crucial role in consciousness and arousal. Damage to specific thalamic regions can cause coma or profound alterations in awareness, demonstrating its importance beyond simple information relay. During sleep, the thalamus reduces the flow of sensory information to the cortex, creating the sensory disconnection that characterizes deep sleep, even though your senses continue functioning. The relay station at the center of your brain, sorting and directing the constant stream of sensation flowing from your body to your mind, deciding what deserves conscious attention and what can be handled automatically, shaping your experience by choosing what information reaches awareness and what remains beneath it. Memories are not stored in single locations but distributed across multiple brain regions as interconnected networks. When you remember an event, your brain reconstructs it by reactivating the same regions that were active during the original experience. Visual cortex for what you saw, auditory cortex for what you heard, motor cortex for movements you made. This distributed storage means memories are not like videos stored in a file, but rather like patterns that must be recreated each time you remember, which is why memories can change over time, details shifting or being embellished with each recall. The hippocampus helps coordinate these distributed networks, binding together the different elements of an experience into a coherent memory, but the actual information is stored in the cortical regions that originally processed it. As memories age, they become less dependent on the hippocampus and more dependent on cortical storage, gradually transitioning from fragile new memories that can be easily disrupted to stable long-term memories that can last decades. This distributed system makes memory robust. Damage to one brain region might eliminate certain aspects of a memory while leaving others intact, the experience partially surviving even when parts of the network are lost. Your memories live not in any single place, but in the relationships between regions, in patterns of connection that span your entire brain, each recollection an act of creation rather than simple retrieval, your past constantly being reconstructed from distributed pieces scattered across the landscape of your cortex. The brain processes negative experiences more thoroughly than positive ones, an evolutionary survival mechanism. Bad experiences, threats and dangers and failures receive more attention and are remembered more vividly than good experiences because in ancestral environments, the cost of ignoring danger was much higher than the cost of missing an opportunity. This negativity bias means your brain dedicates more resources to processing and remembering negative information, scanning for threats more actively than for rewards, a tendency that helped ancestors survive but can contribute to anxiety and depression in modern environments where actual threats are rare. Studies show that people need multiple positive experiences to outweigh a single negative one, the ratio varying depending on context but generally favoring negative information in both attention and memory. The amygdala responds more strongly to negative stimuli than to positive ones, and negative memories are more likely to be consolidated into long-term storage than positive memories of similar intensity. This bias shaped behavior over millions of years. Organisms that paid more attention to dangers survived and reproduced, while those who ignored threats died out, leaving us descended from ancestors who were vigilantly negative. Understanding this bias can help you counteract it consciously, deliberately focusing on positive experiences to balance the brain's natural tendency toward the negative, working against your own neural architecture in service of greater happiness and well-being. Your sense of self emerges from activity across multiple brain networks rather than a single location. There is no one place in the brain where you live, no central theater where consciousness happens. Instead, your sense of being a unified self arises from the coordinated activity of many regions working together. The medial prefrontal cortex helps process self-referential thought. The posterior cingulate cortex contributes to autobiographical memory. The insula processes internal body states, and the temporoparietal junction helps distinguish self from other, all of these combining to create the feeling of being you. This distributed sense of self explains why brain damage can alter personality and self-awareness in profound ways. Different types of damage disrupting different aspects of selfhood depending on which regions are affected. The self is not a fixed thing, but a process, constantly being generated by your brain through the integration of memory, sensation, and thought into a coherent narrative of identity and continuity. Meditation studies show that practices that reduce activity in self-referential brain networks can lead to experiences of selflessness or ego dissolution, suggesting that the strong sense of self we normally feel is actively maintained by neural activity rather than being a fundamental feature of consciousness. You are not located in any particular place in your brain, but rather emerge from the entire pattern of activity across regions, a process rather than a place, constantly being created and recreated moment by moment. The brain's reward system can respond to anticipated pleasure as strongly as to actual pleasure. When you look forward to something enjoyable, dopamine neurons activate and create feelings of pleasure and motivation, sometimes more powerfully than the actual experience when it arrives. This anticipatory pleasure explains why waiting for a vacation can be more enjoyable than the vacation itself, why looking forward to a meal can be as satisfying as eating it, the brain getting a reward both from anticipation and from actual experience. The reward system evolved to motivate seeking behavior, to make animals actively search for food and mates rather than passively waiting. So anticipation of reward became rewarding itself to drive this active searching. This can create disappointment when reality doesn't match expectation, the anticipated reward that drove motivation sometimes exceeding what the actual experience delivers, leaving you let down despite achieving what you wanted. The power of anticipated pleasure is also why delayed gratification is so difficult. The immediate reward of eating the cookie now releases dopamine right away, while the abstract future reward of better health releases less dopamine in the present. Your brain responding to what might happen almost as much as to what is happening, creating hope and motivation from possibilities and expectations, living simultaneously in the present and in imagined futures that may never arrive but feel real enough to drive behavior and create emotion. Neurons that fire together wire together, strengthening connections through repeated use. This principle, often called Hebbian learning after neuroscientist Donald Hebb, who proposed it, explains how learning and memory work at the cellular level, synapses growing stronger when the neurons they connect are active at the same time. When you practice a skill or repeat an experience, the same neurons activate together repeatedly, and this correlated activity triggers changes that make their connection stronger, signals passing more easily each time. This mechanism allows the brain to learn patterns and associations, to link cause and effect, to build skills through practice, each repetition strengthening the neural pathway a little more until it becomes automatic. The opposite is also true. Neurons that stop firing together gradually weaken their connection, which is why unused skills fade and forgotten memories disappear. The synapses between those neurons shrinking and eventually being eliminated. This simple rule, fire together, wire together, underlies the brain's remarkable plasticity, its ability to change throughout life based on experience, to learn and adapt and optimize itself for whatever challenges you face. Every skill you've mastered, every habit you've formed, every association you've learned exists because certain neurons fired together repeatedly and wired themselves into a stronger connection. Your brain physically changing to reflect your experiences, becoming a map of everything you've practiced and everything you've lived. The hypothalamus, though tiny, regulates hunger, thirst, body temperature, and sleep cycles. This small region at the base of the brain, roughly the size of an almond, functions as your body's master regulator, monitoring internal states and making constant adjustments to maintain homeostasis. The hypothalamus receives information about blood sugar, fluid balance, core temperature, hormone levels, and countless other variables, then responds by triggering appropriate behaviors and physiological changes. When your blood sugar drops, the hypothalamus generates feelings of hunger. When your body temperature rises, it triggers sweating and the urge to seek shade, maintaining the narrow ranges necessary for survival. The hypothalamus also controls the pituitary gland, which regulates hormone release throughout the body, making this tiny brain region the command center for the entire endocrine system. Despite weighing only about 4 grams, less than a teaspoon of sugar, the hypothalamus exerts enormous influence over your daily experience, creating drives and needs that motivate behavior, maintaining the delicate balance that keeps you alive. The feeling of thirst on a hot day, the urgent need for sleep when you've been awake too long, the shivering when you're cold, and the satisfaction when you're fed, all of these emerge from this small structure working to keep your body's systems balanced, a tiny regulator with vast responsibilities operating beneath conscious awareness. Your brain recognizes faces using specialized regions that can identify someone in a fraction of a second. The fusiform face area and other regions of the temporal lobe are dedicated primarily to face processing, developing expertise at distinguishing between faces through years of experience. Humans are born with a preference for looking at face-like patterns. Even newborns will look longer at arrangements of shapes that resemble faces than at random patterns, suggesting the brain is predisposed to attend to faces from the very beginning. This specialization allows you to recognize thousands of different faces, to distinguish between very similar faces, to identify people from just a glimpse of their profile, all skills that would be impossible without dedicated neural hardware for face processing. Damage to the face area can cause prosopagnosia, face blindness, where people cannot recognize even familiar faces despite having normal vision and normal ability to recognize other objects. The brain processes faces differently than other objects, paying special attention to the configuration of features and the relationships between them rather than just individual elements, using specialized strategies that only work for faces. This neural specialization for faces reflects how socially important facial recognition has been throughout human evolution, identifying friends and family and potential threats based on facial features, your brain dedicating significant resources to this one category of visual processing that matters so much for social life. The Broca's area in the left frontal lobe is crucial for producing speech. This region, named after French physician Paul Broca, who discovered it in the 1860s, coordinates the complex motor movements required to produce language, organizing the precise timing and sequence of tongue, lip, and vocal cord movements that create speech sounds. Damage to Broca's area causes a specific type of aphasia where people can understand language normally but struggle to produce it, their speech becoming slow and effortful with simplified grammar, even though they know what they want to say. The discovery of Broca's area was one of the first pieces of evidence that specific brain regions handle specific functions, that the brain is organized rather than being a uniform mass of tissue. Broca's area doesn't work alone, but connects to many other regions including motor cortex, auditory cortex, and other language areas, forming networks that coordinate the complex process of turning thoughts into spoken words. Modern brain imaging shows that Broca's area activates not just during speech production but also during certain types of language comprehension, particularly processing grammar and sentence structure, suggesting its role is broader than just motor control. This small region in your left frontal lobe, just a few cubic centimeters of tissue, contains the machinery that allows you to express your thoughts in words, to share your internal experience with others through the intricate code of language. Wernicke's area in the temporal lobe helps you understand spoken and written language. This region, named after German physician Karl Wernicke, processes the meaning of words and sentences, allowing you to comprehend language whether you hear it spoken or see it written. Damage to Wernicke's area creates a different type of aphasia than Broca's area damage. People with Wernicke's aphasia can produce fluent speech with normal grammar and rhythm, but the words don't make sense, and they cannot understand what others say to them. The discovery that comprehension and production of language could be separately damaged showed that language involves multiple specialized regions working together rather than a single language center. Wernicke's area connects to auditory cortex for processing speech sounds and to visual cortex for processing written words, integrating these inputs with stored knowledge about word meanings and relationships. The region develops through language exposure during childhood, its organization shaped by the specific language or languages you learn, different languages activating slightly different patterns even though they use the same general area. Understanding language seems effortless, words arriving as meaning without conscious processing. But this automatic comprehension depends on Wernicke's area rapidly matching incoming sounds or letters to stored representations and activating associated concepts, working so efficiently that the complex computations become invisible. The brain processes music using both hemispheres, unlike language, which is typically left hemisphere dominant. Music engages widespread networks including auditory cortex for processing sound, motor areas for rhythm and movement, emotional centers for the feelings music evokes, and memory systems for recognizing familiar songs. The right hemisphere appears more involved in processing melody and pitch, while the left hemisphere handles rhythm and temporal aspects, though both sides contribute to the complete musical experience. Musicians show interesting brain differences from non-musicians, years of practice literally changing brain structure and function, enlarging areas involved in fine motor control and auditory processing, demonstrating dramatic plasticity in response to musical training. Music can affect people with brain damage in surprising ways, sometimes allowing people with aphasia who cannot speak to sing lyrics perfectly, or helping people with Parkinson's disease who struggle to walk to move more easily when music is playing. The emotional power of music appears to involve connections between auditory cortex and limbic structures like the amygdala and nucleus accumbens, allowing sound to evoke powerful feelings without any words or explicit meaning. Music engages your brain more completely than almost any other activity, simultaneously activating sensory processing, motor control, memory, and emotion, creating experiences that are somehow more than the sum of these parts. Meditation can increase gray matter density in areas associated with learning, memory, and emotional regulation. Studies of long-term meditators show structural brain changes, particularly in the hippocampus and prefrontal cortex, regions that are often larger and denser in people who meditate regularly compared to non-meditators. Even relatively brief meditation training, just 8 weeks of daily practice, can produce measurable increases in gray matter density in these regions, demonstrating that meditation doesn't require decades to create structural changes. Meditation also appears to reduce activity in the default mode network and strengthen connections between prefrontal cortex and amygdala, potentially explaining why meditation can reduce anxiety and improve emotional regulation. The brain changes associated with meditation suggest it's not just a temporary state, but a skill that literally reshapes neural architecture, creating lasting changes in how the brain processes attention, emotion, and self-referential thought. Different types of meditation, focused attention versus open monitoring versus loving kindness, activate different brain networks and may lead to different structural changes, suggesting meditation is not one thing but a family of practices with varying neural effects. Regular meditation training is essentially practice at controlling attention and awareness, and like any practiced skill, it strengthens the neural circuits involved, making those circuits more efficient and increasing gray matter in regions that support meditative abilities. The brain's glymphatic system clears waste products during sleep, particularly deep sleep. This system, discovered only recently in 2012, uses cerebrospinal fluid to flush metabolic waste from brain tissue, working like a waste removal service that operates primarily at night. During sleep, the space between brain cells expands by up to 60%, allowing cerebrospinal fluid to flow more easily through tissue and carry away accumulated toxins, including beta amyloid, a protein that can build up and contribute to Alzheimer's disease. This cleaning process is much less active during waking hours, suggesting one important function of sleep is simply to give the brain time to take out the garbage, removing the waste products that accumulate during the day's neural activity. Chronic sleep deprivation may interfere with this cleaning process, potentially allowing toxic proteins to accumulate over time and increasing the risk of neurodegenerative diseases. The glymphatic system provides a concrete mechanism explaining why sleep is essential for brain health, not just for memory consolidation or energy restoration, but for literal physical cleaning of the tissue. While you sleep, cerebrospinal fluid is washing through your brain, carrying away the cellular debris left behind by billions of neurons working throughout the day, maintaining the clean environment necessary for healthy neural function. Your brain perceives time differently depending on age, stress, and novelty of experiences. Time seems to pass more slowly in childhood and more quickly with age, a phenomenon that may result from differences in how much processing the brain has to do, novel experiences requiring more attention and creating more detailed memories that make time feel extended. When you're stressed or in danger, time can seem to slow down as your brain increases its processing speed, capturing more details per unit of real time in an attempt to deal with the threat, creating memories that are so detailed they make the event seem longer in retrospect. Familiar, routine experiences seem to pass quickly because your brain processes them efficiently without much attention, fewer memories being formed and therefore less subjective time passing. This variability in time perception shows that your experience of time is constructed by your brain rather than being a direct perception of external reality, the same objective duration feeling different depending on what your brain is doing. Time perception also depends on attention. Watching the clock makes time pass slowly, while being absorbed in an activity makes hours vanish. Your brain measuring duration partly through how much it notices rather than through any internal clock. Your entire life's timeline exists only in your memory, the present moment constantly slipping into past as new moments arrive, and the way your brain processes and stores these moments determines whether your life feels long or short, full or empty, rich with experience or monotonously similar. The insula processes internal body sensations and helps create emotional awareness. This region, hidden in the folds between the frontal and temporal lobes, receives signals from your internal organs and integrates them into conscious awareness, creating the felt sense of your body's internal state. The insula helps you feel your heartbeat, notice your breathing, sense tension in your muscles, detect nausea or hunger, bringing all these bodily signals into awareness and contributing to emotions which are partly composed of these physical sensations. Some researchers believe the insula is crucial for consciousness itself, that the sense of being an embodied self depends on the insula integrating signals from throughout the body into a unified sense of physical existence. The insula activates during empathy when you witness others' pain or disgust, suggesting it helps you understand others' feelings by simulating those feelings in your own body, creating a visceral understanding of others' states. Damage to the insula can reduce emotional awareness and the ability to sense internal body states, sometimes leading to conditions where people cannot feel their own heartbeat or sense their body's physiological responses. The insula connects body and mind, transforming physical sensations into conscious feelings, allowing you to know not just that your heart is beating faster, but that you feel anxious, not just that your stomach is empty, but that you feel hungry, bridging the gap between physiology and subjective experience. The brain can generate new memories within milliseconds of an experience. The process begins immediately as sensory information arrives, early perceptual processing happening even before you're consciously aware of what you're experiencing. Within milliseconds, patterns of neural activity in sensory cortices begin representing the experience, these patterns being the first stage of memory formation, even though they're still very fragile and temporary. The hippocampus helps stabilize these patterns and bind together the different elements of an experience, visual and auditory and emotional components getting linked into a coherent memory of an event. Most new memories formed this quickly are forgotten just as quickly, only a small fraction of your experiences making it into long-term storage, the brain constantly forming memories and then discarding most of them as unnecessary. The speed of initial memory formation is remarkable. You can remember what you just read in this very sentence, even though you encountered it only seconds ago. Your brain already encoding it into temporary storage that allows you to connect this sentence with the previous one. Memories are forming in your brain right now, patterns of activity representing these words and your thoughts about them. Some of these memories will last seconds before fading. Others will make it to long-term storage, becoming part of the permanent record of your life, and all of it beginning in milliseconds, the first traces of memory appearing almost as quickly as perception itself. Social rejection activates the same brain regions as physical pain. When you feel excluded or rejected, regions like the anterior cingulate cortex and insula become active, the same regions that process the unpleasantness of physical pain, creating a literal hurt that's similar to stubbing your toe or touching something hot. This overlap explains why social pain can feel as intense and real as physical injury, why rejection and exclusion can be truly agonizing despite causing no tissue damage. The connection between social and physical pain may have evolved because social connection was crucial for survival. Being excluded from the group in ancestral environments could be fatal, so the brain evolved to treat social rejection as a serious threat worthy of the same alarm systems used for physical danger. Pain medication like acetaminophen can reduce the intensity of social pain as well as physical pain, demonstrating that the neural systems overlap enough to respond to the same pharmacological interventions. The brain's treatment of social pain as real pain reveals how fundamentally social humans are, how deeply wired for connection that evolution has linked our need for belonging to the same systems that protect us from physical harm. The hurt of rejection or loneliness is not metaphorical or imagined but neurologically real, your brain responding to social loss with the same urgency it responds to physical injury, treating connection and belonging as basic needs like food and safety. The brain's plasticity allows blind individuals to repurpose visual cortex for enhanced hearing or touch. In people who are blind from birth or early childhood, the visual cortex doesn't remain idle, but gets recruited for processing other senses, particularly hearing and touch, becoming active when they read Braille or locate sounds. This cross-modal plasticity demonstrates the brain's remarkable flexibility. Regions normally dedicated to vision can support other functions if vision is unavailable, the brain adapting to make best use of whatever sensory information it receives. Blind individuals often show enhanced abilities in certain auditory and tactile tasks, and brain imaging shows their visual cortex activating during these tasks, suggesting the enhanced abilities depend on recruiting extra neural real estate to help process sound and touch. This reorganization begins early in development, the young brain being especially plastic and able to rewire itself dramatically based on available input, though some plasticity persists into adulthood. The phenomenon shows that brain regions are not absolutely committed to specific functions but rather shaped by the input they receive, becoming specialized for vision in typical development but capable of serving other functions when vision is absent. Your visual cortex, the region at the back of your brain reading these words right now, exists in its current form because you have working eyes. In a different body with different circumstances, those same neurons might have become expert at processing sound or touch, instead demonstrating that brain function emerges from the interaction between neural hardware and sensory experience. Alcohol interferes with the hippocampus, which is why intoxication impairs memory formation. When you drink enough alcohol to get drunk, it disrupts the normal functioning of the hippocampus, making it difficult or impossible to form new long-term memories, even though short-term memory remains relatively intact. This is why people can seem relatively functional while drinking, able to carry on conversations and perform tasks, but later have no memory of what happened, the memories simply never getting encoded in the first place. The phenomenon called blackout occurs at higher levels of intoxication when the hippocampus becomes so impaired that memory formation stops almost completely, creating periods where the person was conscious and active but later has no recollection whatsoever. The hippocampus is particularly vulnerable to alcohol because it contains many receptors for neurotransmitters that alcohol affects, and because memory formation is a delicate process easily disrupted by chemical interference. Chronic heavy drinking can cause permanent damage to the hippocampus, shrinking its volume and impairing memory even when sober, one of many ways alcohol can cause lasting brain changes. The memory impairment from alcohol happens in real time as you drink, the memories you might have formed simply vanishing before they're stored, leaving gaps in your personal history, periods of consciousness that leave no trace, experience that happens but doesn't persist in the record of your life. The brain prioritizes recent memories over older ones during initial encoding, a phenomenon called the recency effect. When you try to remember a list of items or a series of events, you typically recall the most recent ones best, those final items still active in working memory and not yet subject to the interference of intervening information. This recency advantage applies to immediate recall. If you wait even a few seconds before trying to remember, the recency effect diminishes and the last items lose their advantage. The brain also shows a primacy effect, remembering the first items in a sequence better than middle items, possibly because early items get more rehearsal and attention before later items arrive. Together, primacy and recency create a U-shaped curve of memory, with beginning and end remembered better than the middle, a pattern that appears consistently across many types of memory tasks. The recency effect demonstrates that memory is not a simple recording, but a dynamic process influenced by factors like attention, rehearsal, and interference, with information in different states of processing having different likelihoods of being remembered. What you experienced most recently exists in a privileged state in your brain right now, still active in neural circuits, not yet committed to long-term storage, but more accessible than anything further in the past, the most recent moments having a quality of presence that older memories lack, still lingering in the transitional space between perception and permanent storage. Your brain creates detailed false memories with the same neural signatures as true memories. When you remember something that never happened, the neural activity looks essentially identical to when you remember something real, the brain activating the same regions and showing the same patterns whether the memory is accurate or invented. False memories can be created through suggestion, imagination, or simply through the reconstructive nature of memory, each recall potentially altering the memory slightly until it diverges from the original experience. The similarity between true and false memories at the neural level explains why people can be completely confident in memories that are partially or entirely wrong. The subjective experience of remembering feels the same regardless of accuracy. Research shows that asking people to imagine events can sometimes make them later believe those imagined events actually happened. The act of imagination creating neural traces similar enough to memory traces that the brain later confuses them. Your memory is not a video recording but a reconstruction, your brain piecing together fragments of actual experience with expectations, suggestions, and imagination, creating a coherent narrative that may or may not accurately reflect what originally happened. Every memory you have could potentially contain false elements, details your brain filled in or distorted without your awareness, and you would have no way to tell just from the memory itself whether it's accurate or altered. The neural traces of truth and fiction being indistinguishable in the subjective experience of remembering. The brainstem contains the pons, which helps regulate sleep and arousal. This bridge-like structure in the brainstem connects the medulla below to the midbrain above, serving as a critical relay station for signals traveling between brain and body. The pons helps control the transitions between waking, REM sleep, and non-REM sleep, coordinating the complex changes in brain activity that characterize different sleep stages. During REM sleep, the pons triggers the muscle paralysis that prevents you from acting out your dreams, sending signals down the spinal cord that inhibit motor neurons and keep your body still while your brain is highly active. The pons also contains nuclei that help regulate breathing, working with the medulla to maintain the rhythm of inhalation and exhalation even during sleep. Damage to the pons can disrupt sleep-wake cycles, cause breathing problems, or impair the muscle paralysis during REM sleep, leading to conditions where people physically act out their dreams. This small structure, just a few centimeters of brainstem tissue, plays an outsized role in regulating consciousness states, coordinating the daily transitions between waking and sleeping that organize your life into the familiar rhythm of days and nights. Glia cells, once thought passive, actively participate in information processing and immune function. These cells, which outnumber neurons roughly 1-to-1 overall, were long dismissed as mere support cells, but research has revealed they play active roles in brain function and health. Astrocytes regulate neurotransmitter levels and blood flow. Microglia serve as the brain's immune cells, clearing debris and fighting infection. And oligodendrocytes produce the myelin that speeds neural signals. Recent discoveries show that astrocytes can release neurotransmitters themselves and modulate synaptic transmission, essentially participating in neural signaling rather than just supporting it passively. Glia also communicate with each other through calcium waves, creating their own information networks parallel to neuronal networks, though the function of glial communication remains partly mysterious. Microglia actively survey the brain for damage and infection, their processes constantly extending and retracting as they patrol their territory, ready to respond to any signs of trouble. The changing understanding of glia reflects how much remains unknown about the brain, entire categories of cells being revealed to have functions far beyond what scientists initially believed. The supporting cast turning out to play crucial roles in the main story of consciousness and cognition. The brain's language centers can shift to the right hemisphere if the left is damaged early in childhood. This remarkable plasticity demonstrates how flexibly the young brain can reorganize, regions that normally develop for language in the left hemisphere successfully establishing themselves in the right hemisphere when the left side is damaged. Children who have the entire left hemisphere removed surgically to treat severe epilepsy can still develop language abilities, the right hemisphere taking over functions it wouldn't normally handle, creating nearly normal language despite having only half a brain. This reorganization is most successful if damage occurs early, before language is fully established, the young brain's plasticity allowing dramatic compensations that become less possible with age. The same severe left hemisphere damage in adults would cause permanent aphasia, the adult brain lacking the plasticity to shift language to new regions, demonstrating how developmental timing affects the brain's ability to recover from injury. This plasticity suggests that the brain's regional specialization, while typical and consistent across most people, is not absolutely hardwired but rather guided by developmental programs that can be modified by circumstances. Language normally developing in the left hemisphere not because that region is uniquely designed for language but because developmental cascades typically unfold that way, cascades that can be redirected when necessary, the brain finding alternative routes to essential functions. Your brain fills in blind spots in vision automatically, creating seamless perception. Each eye has a blind spot where the optic nerve exits the retina, a region with no photoreceptors that cannot detect light. Yet you never notice this gap in your visual field because your brain fills it in based on surrounding information. The filling in process is so seamless that the blind spot is invisible unless you specifically test for it, your brain creating the missing information so skillfully that the fabricated portion is indistinguishable from actual perception. This constant editing extends beyond just the blind spot, your brain continuously constructing visual experience from incomplete information, filling gaps, stabilizing images despite eye movements, creating the impression of a complete, stable visual world from fragmentary and constantly changing input. The brain prioritizes consistency and continuity over accuracy, preferring to guess what's probably there rather than leave gaps in perception, creating a smooth experience even when the underlying information is incomplete. You never see reality directly, but rather see your brain's best interpretation of the sensory data it receives. A constructed model of the world rather than the world itself, edited and filled in and stabilized to create the seamless experience of vision that feels like direct perception but is actually elaborate processing. The nucleus accumbens processes reward anticipation and plays a role in addiction. This small region deep in the forebrain lights up with activity when you expect something pleasurable, releasing dopamine in response to reward-predicting cues even before the actual reward arrives. The nucleus accumbens is part of the mesolimbic reward pathway, sometimes called the brain's pleasure center, though it's more accurately described as a motivation center that drives seeking behavior. Addictive substances and behaviors hijack this system, triggering dopamine release more powerfully than natural rewards, essentially overloading the circuits that evolved to motivate survival behaviors like eating and mating. With repeated drug use or compulsive behaviors, the nucleus accumbens becomes sensitized to drug-related cues and desensitized to natural rewards, creating a state where drugs are intensely motivating while normal pleasures lose their appeal. The nucleus accumbens doesn't just respond to rewards but also learns which actions lead to rewards, gradually shaping behavior to maximize reward acquisition, for better or worse. Understanding the role of the nucleus accumbens in addiction has led to treatments targeting this region or its connections, attempting to restore normal reward processing and reduce compulsive drug-seeking behavior. Stress hormones can enhance memory formation for emotionally significant events. When something important or threatening happens, the amygdala triggers the release of stress hormones like cortisol and adrenaline, and these hormones strengthen memory consolidation in the hippocampus, ensuring that significant events are remembered vividly. This enhancement explains why you can remember exactly where you were during major life events or emergencies, the emotional arousal at the time creating stronger, more detailed memories than normal experiences generate. The system evolved to help animals remember dangers and important learning experiences, enhancing memory for events that matter for survival while letting trivial details fade. However, this same system can create problems. Traumatic experiences can be remembered too well, the enhanced consolidation creating intrusive memories that are difficult to forget, contributing to conditions like PTSD. The relationship between stress and memory is an inverted U. Moderate stress enhances memory while severe stress can impair it. The same hormones that strengthen consolidation at moderate levels, disrupting memory formation when they reach very high concentrations. Your most vivid memories probably involve strong emotions, positive or negative, those moments stamped into long-term storage more deeply than countless ordinary experiences, your brain prioritizing the emotionally significant over the mundane in deciding what deserves to be permanently remembered. The prefrontal cortex helps regulate impulses and make long-term decisions over immediate gratification. This region at the very front of your brain, the last to develop and the first to decline with age, provides what psychologists call executive function, the ability to control impulses, plan for the future, and choose delayed rewards over immediate ones. The prefrontal cortex can inhibit impulses generated by other brain regions like the amygdala or nucleus accumbens, creating the capacity to stop yourself from doing what you immediately want in service of longer-term goals. This self-control depends on having a functioning prefrontal cortex. Damage to this region or factors that impair it, like stress, sleep deprivation, or alcohol, can reduce impulse control and make it harder to resist temptation. The prefrontal cortex is also involved in holding future consequences in mind when making decisions, imagining how you'll feel tomorrow if you indulge today, allowing consideration of delayed outcomes that aren't immediately present. The slow development of the prefrontal cortex explains why children and adolescents struggle more with impulse control than adults. This regulatory system still under construction through the teenage years. Every time you choose the harder path because it's better in the long run, every time you resist an impulse because of future consequences, your prefrontal cortex is active, working against more primitive brain systems that prioritize immediate rewards, providing the neural basis for willpower and self-control. Your brain uses contextual clues to interpret ambiguous sensory information constantly. Most sensory input is inherently ambiguous. The same sound or image could be interpreted multiple ways, and your brain uses context, expectations, and prior knowledge to resolve these ambiguities and create coherent perception. This is why you can recognize words in noisy environments, your brain using the context of the sentence to guess at words you couldn't hear clearly, or why optical illusions work, the brain making assumptions based on typical contexts that can be violated to create surprising effects. Perception is not passive reception but active interpretation. Your brain constantly making educated guesses about what's out there based on limited and ambiguous information, usually getting it right because the guesses are informed by experience and context. Top-down processing, where expectations and knowledge shape perception, is just as important as bottom-up processing, where sensory data drives perception, the two working together to create your experience of the world. This dependence on context means your perception can be manipulated by changing the context, the same physical stimulus producing different perceptions depending on what surrounds it, demonstrating that what you see and hear and feel is determined as much by your brain's interpretations as by the actual sensory input. You never perceive the world directly, but always through the filter of interpretation, your brain creating meaning from ambiguous signals, using context to make sense of sensation. The superior colliculus coordinates rapid eye movements toward visual targets. This structure in the midbrain helps orient your eyes and head toward interesting stimuli, working below conscious awareness to direct attention to movement or sudden changes in the visual field. When something moves in your peripheral vision, the superior colliculus can trigger a reflexive eye movement toward it before you consciously register what you saw, a rapid orienting response that helped ancestors detect predators and prey. The superior colliculus receives direct input from the retina and can trigger eye movements faster than cortical visual processing allows, providing a quick and dirty response system that operates in parallel with more detailed cortical analysis. This rapid orienting is one reason it's hard to ignore sudden movements in your visual field, the superior colliculus automatically directing your gaze toward them before you decide whether they're worth attending to. The structure also integrates information from multiple senses, responding to sounds and touch as well as vision, helping coordinate orientation towards stimuli regardless of which sense detects them. Every quick glance toward a movement, every reflexive turn of your eyes towards something unexpected involves the superior colliculus working in the background, directing your attention to potentially important information before your conscious mind has processed what's happening. Brain waves during deep sleep oscillate at 0.5 to 4 cycles per second, the slowest frequency. These delta waves reflect synchronized activity across large populations of neurons, rising and falling together in slow rhythms that characterize the deepest stages of sleep. During deep sleep, these slow oscillations help coordinate memory consolidation and the glymphatic clearing we discussed earlier, the brain using this synchronized state to perform maintenance that's difficult during the faster, more chaotic activity of waking. The slow waves of deep sleep appear most prominently in the first third of the night, gradually declining as sleep progresses and REM periods become longer and more frequent. Deep sleep is the hardest stage to wake from, your brain deeply disconnected from external stimuli, the slow oscillations reflecting a state far removed from the rapid, desynchronized activity of consciousness. The amount of deep sleep you get decreases with age, older adults spending less time in these slowest frequencies and more time in lighter stages, one reason why sleep may become less restorative as you age. Tonight, as you drift from lighter sleep into the deepest stages, your brain waves will gradually slow, billions of neurons beginning to oscillate in unison, creating the slow, synchronized rhythms that characterize the most profound disconnection from the waking world. The cingulate cortex helps detect errors and conflicts in processing, signaling when attention is needed. This band of cortex that wraps around the corpus callosum contains neurons that activate when something goes wrong, when you make a mistake, or when two pieces of information conflict, essentially serving as the brain's error detection system. The anterior cingulate cortex particularly responds to conflict and uncertainty, activating when you need to choose between competing options or when outcomes are worse than expected. This region communicates with prefrontal cortex and other areas to recruit additional cognitive control when simple automatic processing isn't sufficient, calling for more careful attention when situations are difficult or ambiguous. The cingulate cortex is also involved in pain processing and emotional regulation, its position between limbic emotional structures and cortical reasoning areas allowing it to integrate emotion and cognition. Increased activity in the anterior cingulate cortex appears in anxiety disorders and OCD, possibly reflecting an overactive error detection system that sees problems and conflicts even in safe or routine situations. Every time you notice a mistake, feel uncertain about a decision, or experience internal conflict between what you want to do and what you should do, your cingulate cortex is active, monitoring your mental processes and flagging situations that require more careful thought and control. Your brain processes touch sensations in a map-like representation called the sensory homunculus. In the somatosensory cortex, different regions process touch information from different body parts, creating a distorted map where sensitive areas like hands and face take up much more space than less sensitive areas like the back or legs. If you could see this map, it would look bizarre. A human figure with enormous hands and lips, tiny arms and legs, the proportions reflecting sensory importance rather than physical size. This map is not fixed but can change based on experience. People who read Braille develop larger cortical representations of their reading finger. Musicians develop enlarged representations of their instrument-playing fingers, the map expanding for body parts that are used intensively. Phantom limbs after amputation may result partly from the persistence of this map, the brain region that used to process the missing limb still present and still capable of generating sensations when activated. The homunculus demonstrates again that the brain doesn't simply mirror reality, but creates practical representations optimized for function rather than accuracy, dedicating more processing power to fingertips that manipulate objects than to backs that just need to detect pressure. Your brain's map of your body is drawn not in physical proportions but in importance and sensitivity, a functional representation that makes you better able to use your hands and feel your face than to sense your elbows or ankles. Oxytocin released in the brain promotes bonding, trust, and social connection. This hormone, produced in the hypothalamus and released into the brain during social interactions, childbirth, and breastfeeding, helps create the feelings of warmth and connection that bind people together. Oxytocin reduces activity in the amygdala and reduces stress responses, creating a sense of safety and calm that facilitates social bonding and trust. The hormone is released during positive social interactions, particularly physical touch, creating a feedback loop where connection triggers oxytocin, which promotes more connection, strengthening social bonds through neurochemical reinforcement. Parent-child bonding depends partly on oxytocin, the hormone surging during childbirth and breastfeeding, helping create the intense attachment between mother and baby that ensures parental care. Romantic partners also show oxytocin increases during intimacy, the hormone contributing to the feelings of love and attachment that maintain relationships. However, oxytocin's effects aren't universally positive. It can also increase defensive aggression toward outsiders while promoting bonds within groups, essentially strengthening in-group favoritism. The role of oxytocin in bonding reveals that love and attachment have neurochemical foundations, feelings that seem purely emotional actually depending on molecular signals in the brain, the warmth of connection emerging from this small molecule promoting trust and togetherness. The brain's temporal lobes are crucial for processing auditory information and forming long-term memories. The temporal lobes on the sides of your brain contain both the primary auditory cortex, which processes sounds, and the hippocampus and surrounding structures crucial for memory formation. This proximity is not accidental. The temporal lobe's position allows tight integration between hearing and memory, helping you remember what you hear and recognize familiar sounds and voices. The temporal lobe also processes language comprehension through Wernicke's area and recognizes faces and objects through regions on the underside of the temporal cortex, making this one of the most functionally diverse areas of the brain. Damage to temporal lobes, particularly on both sides, can cause profound amnesia, destroying the ability to form new long-term memories, even though short-term memory and other cognitive functions remain intact. The temporal lobes expand significantly during human evolution, our need for complex language and extensive memory requiring more neural real estate than our primate relatives possess. The sounds entering your ears right now, if there are any, are being processed in your temporal lobes, patterns of neural activity representing those sounds and potentially creating memories that will outlast the sounds themselves, your temporal cortex capturing the auditory world and weaving it into the ongoing narrative of your life. Your brain maintains a sense of proprioception, knowing where your body is in space without looking. This awareness of body position comes from sensors in muscles, tendons, and joints that constantly report to the brain about limb position and movement, creating an internal model of your body's configuration. The somatosensory cortex integrates this proprioceptive information with other sensory input to maintain awareness of body position, allowing you to touch your nose with your eyes closed or walk without constantly looking at your feet. This sense is so automatic and reliable that you only notice it when it fails, when your foot falls asleep and you can't feel where it is, or when certain neurological conditions disrupt proprioception and make coordinated movement difficult. The brain's body model is constantly updated, tracking every movement and maintaining an accurate representation of your posture and position that allows smooth, coordinated action. Proprioception is one of those hidden senses that fundamentally shapes your experience without reaching conscious awareness. You know where your hands are right now without looking. You can feel your posture and the position of your limbs. All of this information available to consciousness without any effort. The brain's ability to track the body's configuration through space is what allows you to move gracefully and interact with objects precisely, an invisible sense that makes embodied existence possible. The caudate nucleus helps form habits by linking actions with outcomes through repetition. This structure, part of the basal ganglia deep in the brain, is crucial for procedural learning, the kind of learning that creates automatic behaviors through practice. When you first learn a new skill, you need to think consciously about each step, but with practice, the caudate nucleus helps encode the sequence as an automatic routine that runs without conscious attention. The caudate processes which actions lead to rewarding outcomes and strengthens the neural pathways for successful action sequences, gradually automating behaviors through trial and error. Habits formed through caudate-based learning can persist even after the original goal is no longer relevant, which is why habits are so hard to break, the learned sequences continuing to run automatically even when they're no longer useful. The caudate also helps you learn categories and rules, recognizing patterns that allow you to generalize from specific experiences to broader principles. Every habit you have, from tying your shoes to your morning routine, involves the caudate nucleus encoding sequences of actions through repetition, creating automatic behaviors that free your conscious mind for other tasks. The trade-off being that these automated sequences can be difficult to modify once established. Your brain generates theta waves during light sleep and deep relaxation, oscillating at 4 to 8 cycles per second. These waves reflect a state between the fully alert beta waves of active thinking and the slow delta waves of deep sleep, a middle frequency associated with meditation, creativity, and the early stages of sleep. Theta activity increases during drowsiness and light sleep, particularly in stage 1 sleep as you're first drifting off, creating the floating, dreamlike quality of that transition between waking and sleeping. The hippocampus generates theta rhythms during certain types of memory processing and spatial navigation. These oscillations thought to coordinate the timing of neural firing to facilitate learning. Meditation can increase theta power, the relaxed but aware state of meditation corresponding to this frequency range that's rare during normal waking consciousness. Theta waves are also prominent in young children, their brains spending more time in this frequency range than adult brains, possibly reflecting the extensive learning and memory consolidation of childhood. Tonight, as you drift towards sleep, your brain waves will shift from the faster frequencies of waking thought through theta range, lingering briefly in this intermediate state before descending further into the slow rhythms of deep sleep. Theta waves marking the boundary between consciousness and sleep. The parietal lobe integrates sensory information to create spatial awareness and navigation ability. This region at the top and back of your brain combines touch, vision, and proprioception to create a coherent sense of space and your body's position within it. The parietal lobe helps you reach for objects accurately, navigate through environments, understand spatial relationships, and perform mental rotation of objects in your imagination. Damage to parietal lobe can cause neglect syndromes where people fail to notice or attend to one side of space, or difficulties with spatial reasoning like getting lost in familiar places or being unable to reach accurately for objects. The parietal lobe also contributes to mathematical reasoning and symbolic thought, suggesting that abstract reasoning may be built on foundations of spatial processing, mathematical concepts emerging from brain regions that originally evolved for navigating physical space. Your sense of being located in space, of knowing where you are and where things are in relation to you, depends on parietal lobe constantly integrating multiple streams of information into a unified spatial map. The parietal cortex is working right now to tell you where you are as you read this, maintaining your sense of position and orientation even though you're not consciously thinking about it, creating the invisible framework of space within which all experience occurs. Your brain processes visual information in a hierarchical manner, from simple edges to complex objects. The visual cortex is organized in stages, early areas in the occipital lobe detecting basic features like oriented edges and colors, while progressively later areas combine these simple features into more complex representations of shapes, objects, and scenes. This hierarchical processing allows the brain to build complex perceptions from simple building blocks, starting with the raw information from the retina and gradually constructing meaningful representations through multiple stages of analysis. Different pathways handle different aspects of vision. The ventral stream flowing toward the temporal lobe processes object identity and recognition, answering what you're seeing, while the dorsal stream flowing toward the parietal lobe processes spatial location and movement, answering where things are. The sophistication of this processing explains why human vision is so good at recognizing objects despite changes in lighting, angle, and distance. The visual system extracting invariant features that remain constant across viewing conditions. Every object you recognize, every face you identify, every scene you understand results from this hierarchical processing. Simple features extracted from light patterns on your retina being progressively combined and refined through multiple cortical areas until meaningful perception emerges, the final result seeming effortless despite the extensive computation required to achieve it. The ventral tegmental area produces dopamine that drives motivation and pleasure. This small region in the midbrain contains dopamine neurons that project widely throughout the brain, particularly to the nucleus accumbens and prefrontal cortex, creating the mesolimbic and mesocortical dopamine pathways. These pathways are crucial for motivation, reward learning, and reinforcement, essentially providing the neural currency that makes certain actions feel worth doing. The VTA's dopamine neurons fire in response to rewards and reward-predicting cues, teaching the brain which actions and situations are valuable and motivating approach and repetition of successful behaviors. Addictive drugs often work by triggering massive dopamine release from the VTA, far more than natural rewards produce, essentially hijacking the motivation system and making drug-seeking behavior overwhelmingly compelling. The VTA's role extends beyond just pleasure to include motivation more broadly. People with reduced VTA dopamine function show symptoms like anhedonia and lack of motivation even if they don't feel particularly sad. This tiny cluster of dopamine-producing neurons, maybe a few millimeters across, exerts enormous influence over what you find rewarding, what motivates you, what makes life feel worth living. The dopamine signals from the VTA providing the neurochemical foundation for desire and drive. Your brain's working memory can typically hold 4 to 7 pieces of information simultaneously. This limited capacity, often described as the magical number 7 plus or minus 2, reflects a fundamental constraint on conscious processing. You can only actively maintain and manipulate a small amount of information at any given moment. Working memory acts like a mental workspace where you hold information temporarily while using it, remembering a phone number long enough to dial it or holding multiple factors in mind while making a decision. The prefrontal cortex and parietal cortex work together to maintain working memory, actively representing information through sustained neural activity that keeps it available to consciousness. This limited capacity explains why complex tasks are difficult, why you can't keep track of too many things at once, why learning becomes harder when too much information arrives simultaneously. The workspace of consciousness simply cannot hold unlimited content. Chunking can expand working memory's effective capacity, grouping individual items into meaningful units, so a phone number becomes 2 or 3 chunks rather than 10 separate digits, using organization to overcome the fundamental limitation. The narrow bottleneck of working memory shapes human cognition profoundly, limiting how much you can think about consciously, forcing you to rely on long-term memory and automated processes for most mental work, conscious attention being a scarce resource that must be allocated carefully. The occipital lobe at the back of the brain is dedicated almost entirely to processing vision. This region contains the primary visual cortex and multiple visual processing areas that analyze different aspects of visual information, creating the neural foundation for sight. The occipital lobe is organized retinotopically, meaning adjacent regions of the visual field are processed by adjacent regions of cortex, creating a map of visual space at the back of your brain. Despite being dedicated to vision, the occipital lobe can be recruited for other purposes if vision is absent, as we discussed earlier, blind individuals using this region for processing sound and touch. The occipital lobe receives most of its input from the eyes via the thalamus, though it also receives feedback from higher visual areas that can modulate processing based on attention and expectation. Damage to primary visual cortex causes cortical blindness, loss of conscious vision even though the eyes and optic nerves remain intact, demonstrating that vision depends on the brain processing visual information, not just the eyes detecting it. Everything you see exists as patterns of activity in your occipital lobe, the visual world you experience being a construction created by this region from the signals arriving from your eyes. Not the world itself, but a neural representation of it, a model built from light. Your brain maintains circadian rhythms through the suprachiasmatic nucleus, responding to light and darkness. This tiny region in the hypothalamus, each side smaller than a grain of rice, contains about 20,000 neurons that function as your body's master clock. The SCN receives direct input from specialized light-sensitive cells in the retina, allowing it to synchronize with the day-night cycle and coordinate circadian rhythms throughout your body. These rhythms influence sleep-wake cycles, hormone release, body temperature, metabolism, and countless other processes that oscillate on roughly 24-hour schedules. The SCN maintains its rhythm even in constant darkness, continuing to cycle with a period of about 24 hours, though light exposure is necessary to keep the rhythm synchronized with actual day length. When you travel across time zones, jet lag results from the SCN being out of sync with local time, requiring several days to gradually shift its timing to match the new schedule. The circadian system coordinates not just sleep, but the timing of virtually all physiological processes, organizing your body's functions around the predictable cycle of day and night that has characterized life on Earth for billions of years. 2 tiny clusters of neurons maintaining the temporal structure of your life, keeping time with the planet's rotation, ensuring you feel alert during the day and sleepy at night, coordinating the intricate choreography of your body's rhythms. The putamen helps coordinate movement and certain types of learning through practice. This structure, part of the basal ganglia along with the caudate nucleus, contributes to motor control and the formation of motor habits through repetition. The putamen receives input from motor cortex and sensory cortex and projects to other basal ganglia structures that ultimately influence motor output, creating loops that refine and automate movements. Procedural learning, the kind that creates skills like riding a bike or playing an instrument, depends heavily on the putamen gradually encoding successful movement sequences through practice. The putamen is also involved in reward processing and reinforcement learning, helping determine which actions should be repeated based on their outcomes. Parkinson's disease affects the putamen and other basal ganglia structures, disrupting their ability to facilitate smooth movements and contributing to the tremor and rigidity characteristic of the condition. Every skilled movement you make, every practiced action that flows automatically, reflects the putamen's contribution to motor learning and control, this structure working with other basal ganglia to translate intentions into smooth, coordinated actions. Your brain's white matter, composed of myelinated axons, continues developing into your 40s and 50s. While grey matter reaches peak volume in childhood or adolescence, white matter continues increasing well into middle age as more axons become myelinated and existing myelin thickens. This prolonged white matter development reflects ongoing refinement of connections between brain regions, improving the speed and efficiency of neural communication throughout adulthood. The continued development of white matter may support the maintenance and even enhancement of certain cognitive abilities in middle age, despite declines in processing speed and working memory, better connectivity compensating for reduced raw processing power. White matter integrity begins declining in later life, contributing to cognitive aging, but the extent and timing of this decline varies greatly between individuals depending on genetics, lifestyle, and health. The fact that white matter continues developing so late demonstrates that brain maturation is not complete in early adulthood, but continues for decades. The brain's connectivity continuing to refine throughout much of the lifespan, neural pathways becoming more efficient even as other aspects of brain function begin to decline. The pineal gland produces melatonin in response to darkness, helping regulate sleep cycles. This small endocrine structure, about the size of a pea, sits deep in the brain and converts serotonin to melatonin when darkness signals from the SCN indicate that night has arrived. Melatonin release increases drowsiness and helps initiate sleep, levels rising in the evening and remaining elevated through the night before dropping in the morning. The pineal gland's response to light and darkness explains why bright light in the evening can delay sleep onset by suppressing melatonin release, and why darkness promotes sleepiness by allowing melatonin to rise. The gland synthesizes melatonin from serotonin in a multi-step process that increases dramatically at night, creating the hormonal signal that coordinates sleep timing with the day-night cycle. The pineal gland's role in sleep regulation has been known since ancient times, though early philosophers like Descartes mistakenly thought it was the seat of the soul, its central position and unique structure making it seem special despite its relatively simple endocrine function. Every night as darkness falls, your pineal gland begins producing melatonin, this small structure helping synchronize your sleep with the rotation of the Earth, maintaining the ancient rhythm that connects your consciousness to the planetary cycle of day and night. Your brain creates your entire experience of consciousness moment by moment, weaving sensation, memory, and imagination into the continuous story of being you. Every color you see, every sound you hear, every thought you think exists only as patterns of neural activity in the 3 pounds of tissue inside your skull, the external world translated into electrical and chemical signals that your brain interprets and experiences. Consciousness emerges from the coordinated activity of billions of neurons, none of them conscious individually, but somehow creating subjective experience through their collective interaction. The unity of consciousness. The feeling that you are a single coherent self experiencing the world from a single point of view is itself a construction, your brain binding together disparate processes into the seamless experience of being. Your brain creates not just perception but reality itself as you experience it, constructing the vivid present moment from fragmentary sensory data, memories of the past, and predictions about the future, weaving all of this into the ongoing narrative of your life. The fact that you exist, that there is something it feels like to be you, that you have subjective experiences rather than simply processing information unconsciously like a computer, remains one of the great mysteries, consciousness emerging from matter in ways we still don't fully understand. And yet it happens. Your brain creates the entire universe of your experience, generates the feeling of being alive and aware, maintains the continuous sense of self that persists from moment to moment, making you not just a collection of cells but a conscious being, experiencing existence from the inside, aware of being aware, thinking about the very brain that makes thinking possible. And so we end where we began, with the quiet mystery of your brain, this organ that has been with you since before birth and will remain until the end, working ceaselessly through the night. Rest now. Let these facts drift away like dreams, your brain continuing its ancient work while you sleep.